Alright, so in the last lecture we discussed the concept of endurance, what exactly it implies, and how traditionally it has been sort of described. So traditionally when I say I am implying the use of aerial vehicles which are using fuel as a power source. So what happens that with time fuel gets consumed and therefore your all of weight or your craft weight uh, comes down, and as a consequence your power required also changes. This is not true about a battery driven system, but battery means we are talking about battery. If I put a fuel cell, this formula will again come back into picture. So, fuel cell is also electric power, but fuel cell actually works in the concept where you have a membrane which is your cell. So, typically they are PEM, your proton exchange membranes, in short form they are called as PEM, and so these act like an engine, and then you have separate storage of hydrogen. So, hydrogen could be stored as in the form of compressed hydrogen or adsorbed on some material and so on. There are many different techniques by which hydrogen could be stored actually on board. So, this now actually is your like a fuel tank, and with time this will get consumed. So, this will work exactly the way your fuel based systems have been working. The only difference is that now instead of your C, which is your specific fuel consumption, which basically implies at what rate you are consuming your fuel, you will have a slightly different number, okay. And it would effectively be of the same kind. The formula for that will be same. It may not be called a C, it may be called something else, where now your fuel is also getting consumed per unit of your power required and per unit of your time. So these formulas are not necessarily not relevant if I go to a battery power system or rather electric power systems or electrically powered UAVs. It is still very relevant, because there are a lot of UAVs which will still use fuel. You have now very popular Shahed drones, they are carrying ton of fuel actually. So, it is very relevant for that, and even if I go with electric power, I can still be powering them through fuel cells, which is true for eVTOLs also. So, now Joby Aviation, they have built this air taxi system which is now getting certified, and it is probably starting operation, or they have done some trial flights in Dubai and all, and these crafts are actually now getting powered by fuel cells. So, even for them these formulas are very relevant. So, we got the basic formula that okay, this is what I need to calculate to get my endurance. So, how does it actually work for a propeller driven airplane? And for us most of the UAVs would be a propeller driven anyway. So, we will only worry about this per se. So, same formula now for a propeller driven system. Now, my dW by Cp has been modified with this. How so? Because my P, normally we think of P as my drag into V infinity, which normally we say thrust required into V infinity, and thrust required and drag are same. But I told you earlier also that this power is not my total power, this is ideal power, and the real power would actually be obtained by factoring in the efficiency factor. How or why? Because when I use a propeller, whatever energy you are putting inside the propeller through your engine or through your motor, entire energy is not getting translated into your forward flight. Okay. So, there is some loss. So, this we denote by using a factor called eta, which is your propeller efficiency. So, this eta P is your propeller efficiency. For larger propellers, this could be as high as 90%, 95%, but 95 is more rare, 90% is more like it. But for smaller propellers, the kind of propellers you will use on small UAVs which are weighing maybe 10 odd kilos, this efficiency could be as low as 65-70%, which means you are going to lose 20 to 30% of your power just like that. Okay. So, this is something to be aware of. So, which means now that my power, so this is my ideal power, if I say by putting a subscript PID, PR which is P real would be P ideal divided by efficiency factor, this eta. You understand how? Because that is the definition of my eta. So, eta P would be P output by P input. Any efficiency for any system is defined like that. What you are putting is an input and what is you are getting as an output. So, output here is my P real and input is my P ideal, which is this d V infinity. Okay. So, P real would be P ideal divided by eta, which is fine, which is eta means P ideal, yeah, right. So, this is actually, sorry, this is P ideal, because that is your, yeah, and this should be P real, yeah.
Higher than 1.
No, this is correct. This is P ideal by P real. P real is more. P ideal is ideal, right? It is less. How it is more? See, this is how it is, right? So that is what actually goes in here. So, my P equals to, so this Cp, P will be equal to d V infinity by eta, and that is what brings you that over here. So, in this integral now I can substitute for the remaining parts. So, what I am doing is that I am dividing this by L. So, what I can do is I can multiply and divide by L. Now, L is also equal to W, because I am flying in steady level condition. So, steady level. So, this is all for steady level flight, remember. So, endurance and range are always defined for steady level flight, not for climbing or descending or any such flight. So, steady level, which means my d equal to PR or sorry, d equals to TR, d equals to TR or P equals to d into V and L equals to W, right. So, these are the things which are already given to me. So, I can multiply and divide by L. So, I can replace one of the L with W. So, now I have L by D and I have dW by W. So, this L by D is a aerodynamic property of my airfoil. So, I can replace that with the non-dimensional ratio CL by CD, and then I end up with dW by W, which I would then integrate, and I end up getting this particular Long's formula, which is in this form. Okay. So, this has my eta is my propeller efficiency, and C is my SFC, rho is of course my density, and W1 W0 we have already defined, which is the total weight and the weight without the fuel, with all the fuel burned basically or consumed, and S is my wing area, okay. And we see that finally this formula actually is dependent on CL to the power 3 by 2 by CD. Okay. So, in this calculation I have not assumed what is my V infinity. I can fly my drone at any speed as long as it is more than the stalling speed. So, this formula represents endurance for any speed possible. So, it is not like it is giving you endurance for only specific speeds, but I can maximize it by maximizing or ensuring that my aircraft operates at maximum CL to the power 3 by 2 by CD. So, we kept telling all the time that the condition for minimum power is max CL to the power 3 by 2 by CD for best endurance or minimum P. Right. So, this we have talked few times already, and that is what actually is coming out in my formula also. If I maximize this particular parameter, my endurance will be maximum, which means I have to ensure that or I select the speed which would operate my aircraft at highest possible CL root CL by CD. or Cl to the power 3 by 2 divided by Cd. So, fine, any questions on this? Yeah.
We are using a fuel cell or fuel instead of battery, which is giving us like more endurance for the same weight. Like if we use a fuel
Possibly, not always true, possibly. Okay, it is not necessarily going to be true all the time. Why? Because yes, I mean if I look at my energy density of fuel, any fuel, I mean you can look at normal gasoline, or you can look at in some cases, like if you use smaller jet engines, there may be some kerosene based derivatives, otherwise not, mostly it is gasoline, or it could be aviation fuel. Aviation fuel is basically high grade gasoline. So, it will be that, or sometimes, I mean for example, Navy does not want you to use gasoline, they prefer you use a derivative of gasoline, which is called, what is the name of that fuel? It is called heavy fuel. It is less combustible actually compared to. So, on board ships you cannot store gasoline, but you can store heavy fuel. So, Navy would say, I mean give us drones which will operate with heavy fuel, not with gasoline, kerosene or any such thing. So, there are already engines available which fly on heavy fuel. So, same engine may have two derivative, one which will be flying with gasoline or other will be flying with a heavy fuel. So, it is not necessary that it will always give you higher endurance, but yes, in general it will if you design it properly, because the energy density of gasoline would be almost 3x or 5x times your typical battery which is there. So, even though your engine may be bulky and heavy, which adds to the weight overall, it is still going to be lighter if you just try to power your UAV purely based on battery alone. So, you need longer endurance, your choices are either to use fuel cells or to use engines. Now, why people are trying to use fuel cells over engine? I mean Joby has built this with fuel cell is still very expensive, not readily available, technology is still about to mature, but they are saying we will use that and we will not use engines. Why? Sure, noise is one consideration, vibration is another consideration, correct, but these two are not necessarily the most important parameters. These are important factors. Yes.
Fuel.
Sorry.
Carriage of fuel.
Well, not so much, because they are civilian operators, right. So, they do not have to worry about it. I mean they are going to operate from airport to airport, they are not going to fly from ship decks per se. So, what other factor is there?
Your like the potency of the fuel compared to its weight.
So, you are again talking about the energy content or the energy density and so on. No, the key driving force for not using fuel, like not using internal combustion engines, is that the challenge of maintaining them. People do not want to make it messy. So, your fuel based engines are messy, they require certain, they have a TBO, time between overhaul. So, after that, I mean you have to overhaul the engine, and these engines, I mean because they are working on very the power to weight ratio, thrust to weight ratio has to be kept very high. So, they do not have all the basic frills which normal your automobile engines have. I gave you example already how automobile engines are so very heavy because they have to meet certain emission standards, and they want to ensure that the cooling is done properly. I mean all kinds of things are taken care of there. Why? Because they want to have a very long life and less requirement for maintenance. So, you can keep driving your car or your two wheeler or four wheeler, and you have to send it, I mean once a 6 months or 1 year or something for your overall maintenance, etc. But for these smaller engines which are there for aviation, some of them are notorious for very regular maintenance, which means it's tricky, and the cost of operation and maintenance becomes very high. This is not there for electric systems, a very little requirement for maintenance, and that actually makes a huge difference, and that is why your helicopters, they can do whatever eVTOLs are going to do. I mean electric vertical lift, your air taxis and so on, they can already do everything what this and better than that actually, but they are very expensive to design, build, manufacture and maintain. More important, maintain and operate. So, maintenance cost and operation cost are a big hindrance for all that. Okay. So, again we are digressing slightly, but something to be kept in mind. So, this is simple for so any fuel based system, even so this would be applicable for fuel cells also. with your C being maybe called something else, but this idea would hold there also. Okay. Now, what happens to the same thing, I mean this formula, if I have a battery powered, a solid battery powered where my weight is not going to change anymore. So, I have a battery powered US, how does my endurance change with that? And it actually becomes very simple to calculate. All I need to do is know my power. Okay, so, I put your power formula here. So, calculate your power required as function of V infinity, your forward speed. So, I simply have to look at this formula, which means power into time is my energy content of my battery. And if I try to understand what exactly is my energy content of a battery, we do not say, I mean we have so many liters of battery, right. We normally denote the battery capacity in terms of ampere hours, okay. But for UAV batteries, because they started with very small size batteries, they started calling it milliampere hours. So, you will have 16,000 milliampere hours. They could very easily say that 16 ampere hours, but they will still write it as 16,000 mAh. Why? Because people only think in mAh. So, that has become now convention. So, you will have batteries going in 50,000 mAh and not say 50 ampere hour, but okay. So, mAh. So, you will normally give battery capacity, it is a capacity, it is not power rating, it is capacity given in milliampere hour. What does it mean? Milli means 10 to the power minus 3, okay. Yeah, I forgot to multiply, this should be multiplied with 10 to the power minus 3 actually. And it would also tell you the number of cells for that battery. So, most of the batteries which are used in UAS world, they are all lithium derivatives. So, you will have lithium polymer batteries, LiPo batteries, lithium ion batteries, lithium solid state batteries, lithium sulfur batteries. So, they are all derivatives of lithium. So, most of them actually have their nominal voltage as 3.7 volt. This is the nominal voltage. So, number of cells n. So, let us say n is number of cells in my battery. So, I can have for moderate size UAVs, you will have 3 to 6 cell batteries in use. For larger UAVs, you will be using 12, minimum 12 to 24, and even larger like manned aerial vehicles, there you operate for 400 volts actually. So, those are 400 or 600 or something like that. But right now up to 150 kg UAV which we are flying, we are still working with 50 volt. 50 volt means 12S, right, 12 into 3.7, yeah. And we actually do want to switch from 12S to 24S. Why? Because it will reduce my current. So, my motor heating will be less. So, that is the idea. So, why we have to actually go to higher number of cells? Because if your voltage increases, because your motor power required would be same. If I give higher voltage, my current will become smaller for the same power. So, that is why you want to go to higher and higher number of cells for larger and larger UAVs. If I make a really tiny UAV, I mean like the toy UAVs which you see, quadcopters which you can buy off the shelf, they would be normally, I mean really tiny ones weighing maybe 100 grams or so, they would be using a single cell battery. Okay. So, it will be just 3.7 volts. You go to slightly bigger scales, maybe 7.4 volts, okay. Even higher 11.1 volts, okay. Then 22.2, like that. So, number of cells I know. So, n multiplied with 3.7 and whatever is your mAh rating. Okay. So, mAh rating if it is say 15,000, okay. So, I will say 15,000 mAh. Now, milliampere hour, milli means 10 to the power minus 3, ampere hour means its current and time. Time is 1 hour has 3600 seconds. So, 3600, 15,000 and 10 to the power minus 3. So, this if I multiply and if my cell is say, so 6 cells. So, if I multiply this will be give me the entire energy content in joules. So, that is the energy I am carrying. But can I use that entire energy? Can I completely deplete my battery? No, I cannot. Okay. Why? Yeah. So, it's we discussed this earlier also. If I deplete it to 0, my battery will die. It may get damaged. So, you would always retain some amount of charge. You cannot really drain the battery entirely. So, most of the bigger UAVs with these batteries, they would have some kind of BMS which will prevent it. So, it is and actually what happens once your battery starts discharging, your nominal voltage also starts dropping. So, when you charge it, it will go to maybe 4.4 or 4.3, right, but once you start using it, you will start dropping, and beyond a point, then I mean your ESC also says, okay, I will not fly anymore, you better come down and land. Okay. So, it will start giving some warning if you start depleting battery beyond a limit actually. Okay. So, you would have to keep some amount of reserve. So, this capacity which I am getting, I would have to multiply with some efficiency factor. Well, it is not really efficiency factor per se, it is more like a reserve factor. Okay. So, this is the entire energy available, but I can only use say 80% of this. So, I will multiply this with 0.8 because I cannot use the remaining 20% if I want to get realistic estimate of my endurance. So, it is better to always claim low. In India, the tendency is that I mean you see any startup and they will claim, oh, I have moon and sun and Mars, everything available. Okay. And when they go for trial, they will not even land earth. Okay. So, the performance will not even be I mean like 50% of what it is there. So, this is a problem for everybody. I mean user actually feels that I mean people are cheating them and you end up cutting a sorry face. So, it is always better to claim less and perform more. So, in the beginning you say, okay, I will only fly for 40 minutes, but you go there and give 60-minute flight. You say, oh, this is fantastic, I mean it is better than I mean, what they claimed, instead of the other way around. Okay. You claim 60 minutes and then they go and fly for 30 minutes only. Okay. So, this is something which you have to keep in mind. So, you want to have realistic estimates about things, not I mean do just empty talking where you do not know what you are actually talking about, right. So, I just need to get this total energy and multiply with some battery factor regarding how much energy is actually available for you to use, and that energy should be equal to your power into time. So, the power required which I will get from this formula. So, I can in effect I can actually if I can plot my power versus velocity graph, I can also plot my endurance versus velocity graph immediately. You get that, because it is just a factor, simple. So, my endurance E is simply my battery energy divided by my power required, and for best endurance, for max endurance I would operate at my lowest power condition. So, that will give me the highest value. So, just like I have my power graph which could be going like this, okay, I would, you can see this is just a reciprocal of my power graph. Okay. So, this is my P versus V infinity. I would get a graph which could probably be going like this, which would be my endurance versus, and the maximum would correspond to the same point which would be the minimum power, right. So, it would probably go like that. So, it is a very simple formula for a battery power system because my weight does not change. So, it just my power is going to remain constant throughout. Yes, your power can change if you are dropping something, if your mission requires that, but then I mean that is not how we define endurance. Endurance we always define for a initial takeoff condition, and then I am not going to change the state of the craft. Okay, your fuel burns, that is a natural process, but I will not say that okay, I mean in my mission I am carrying a payload, so after 10 kilometers I drop the payload and come back. So, I will use that to calculate my endurance. No, that will be incorrect. I mean endurance will be with that weight and without that weight. So, you can say if this is my takeoff weight, this is my endurance, and if I come down to this takeoff weight, this is my endurance. Okay. So, both of them will change your power required. But yeah, if I am designing a UAV and I have to consider the energy required for my entire mission, then I would cater for the actual energy requirement. Energy required when I am carrying the payload, and power and energy required when I am not carrying the payload. So, that actually becomes a separate factor. Okay. So, now that brings us to the next important parameter called range.
If a battery fails, what option we have? Like
Yeah, so that is a good point, but battery, see normally you would have multiple batteries connected in series. You will not have one single monolithic batteries. Okay. So, even if I go to a larger UAV, normally I would actually have multiple cells connected in series or parallel, okay, depending on what condition you are operating at. So, it may so happen that I mean if some battery goes bad, you may still have some other battery which is still powering things up, okay. But yes, you have to have a mechanism to know that okay, my other battery is not available now, okay, it has gone bad. So, there has to be some kind of battery management system which is checking all the cells and things like that. So, you will continuously know your battery state, okay, and some part of battery is not available, I would immediately know that and I will then abort my mission. So, some such mechanism has to be there, but yes, smaller UAVs would have just single battery pack and you would not have any redundancy for that. So, there have been chances where I mean there has been problem especially when you use hobby grade connectors. So, you are flying and there is some problem with the connector and suddenly power goes off, the whole UAV falls from sky pretty much. Okay. So, this is a risk, but with better design and everything these are easily eliminated actually and you use good quality connectors and everything. Okay. Another challenge is that I mean if you use mill grade connectors, it is hard to get high power mill grade connectors and they are very heavy. So, you end up incurring huge weight penalty sometimes. So, that becomes a trade off for you, what do you do? Okay. So, there are, but the key thing is that I mean ideally larger UAVs should have a battery management system, but right now that is not being demanded. Okay. Nobody is demanding for this because already there are so many demands which would not get met. So, this has become a lesser of a priority, but it is something which is critical and the people are getting away because these are uncrewed systems, nobody is there. I cannot do this for a EV, any electric vehicle I mean BMS is an absolute must, BMS stands for battery management system. So, it looks at all the cells, their temperature profile, charging, discharging, life, everything it actually keeps track of. So, these are like intelligent batteries. And interestingly I mean the DJI all their batteries are already equipped with all these capabilities. So, they have been doing this for so long that I mean then and they have made so much money that they could put effort in R&D and build all these technologies. Here I mean we are every day we are struggling to find one solution which user will be able to buy in good number. So, nobody sells more than 120, 50 drones. So, you will never get a time or chance or room to build such technologies over a long period of time. So, it is just serious lack of planning on part of Indian drone ecosystem in that sense. Okay. Alright. So, from endurance we now come to range. Range is, so earlier we talked about with one tank of fuel or one energy source how far or sorry how long can I fly. Now, question is how far can I go with a given tank of fuel or with a given battery. So, range is distance travelled. So, I can call this as dr which is my unit range or range or distance travelled in a unit time infinitesimal time. So, again we assume constant speed. So, it will be V infinity into dt. So, in infinitesimal time dt my speed is constant. So, this is the distance I can travel, which then we have seen dt was related to minus of dw by Cp. So, again we are using a fuel based system where I mean my fuel is getting burnt with time. So, my weight is going to change with time. So, this dr or I can call it as ds distance travelled. So, integral of ds is, so I do the definite integral from W0 to W1, W0 is my initial total weight, W1 is the weight after all my fuel is gone. So, here again I mean it is a theoretical calculation, we are again going to keep some fuel as reserve always, but for theoretical calculation I can assume it to be completely gone. Same way I mean in the previous case also you can for theoretical purpose you can assume it to be gone, but then you should cater for that 20% reduction to give a realistic number. Here that 20% will be much smaller because your fuel has higher energy density. So, finally it will probably knock off only a few minutes in a longer endurance where I mean maybe my endurance is several hours, okay, and my 10-15% fuel reserve would only knock off like some small amount of flight time from that. So, I continue with this integration. So, I have V infinity dw by Cp and that is my range, and this is a general formula which is valid for any category of airplane. It could be jet powered or it could be your propeller driven, either way this formula is valid. Now, we will get a closed form expression for UAV which is driven by propeller, and that formula is named after Louis Breguet, whose name I was mentioning in the last class. So, Louis Breguet was a aviation pioneer, he even tried to build some helicopters also. So, he was the first person to derive this formula and therefore, the name is named after him. So, he also pointed out the same thing, that I mean this power here would be my power required by my efficiency factor, propeller efficiency eta. So, dV infinity by eta. So, this is the power to be delivered by the engine. So, what power? So, when I say power available, we are saying power available to the propeller or power available for propulsion, which means my engine has to give more power, because some power is getting lost in the propeller, okay. Or if there is a mechanical transmission, there could be some mechanical losses also. See, some propeller systems may have gearboxes also. Why? Because the propeller may be operating at a relatively lower RPM, the engine may be operating at a very high RPM, especially jet driven system. So, like, so your jet engines may be operating at 15,000, 20,000 RPM or whatever. My propeller may be only operating at say 3,000 RPM. So, there may be a gearbox also. So, there may be losses due to that also. So, power to be delivered by the engine, and if I substitute that back in my original formula, my range expression becomes integral from W1 to W0, my propeller efficiency eta V infinity dW by C d V infinity. Okay. So, this V infinity and V infinity gets cancelled, but now I will again do the same thing, I will multiply in numerator and denominator with W or lift, and take out L by D separately and retain dW by W. So, now again my L by D is an aerodynamic parameter. So, I can replace that with CL by CD, and eta by C are also constant. So, everything else goes out. So, I can say eta L by or rather CL by, you can write it as eta by C and CL by CD integral from W1 to W0 dW by W, and integral of dW by W is natural logarithm, which gives me this final formula. So, this is Breguet's range formula. I would assume this would be the spelling, French aviation pioneer. So, my range is function of my propeller efficiency, my specific fuel consumption, and my L by D, log natural W0 by W1. So, now you can see the clear evidence why L by D is my propulsive efficiency. If I maximize L by D, I maximize my range. So, L by D directly affects my distance travelled, CL to the power 3 by 2 by CD affects my endurance, flight time. So, these are the two most critical things which you have to absolutely remember, very fundamental thing. Nothing very fancy, very simple, but very critical. It determines, I mean, how your design is actually going to work. So, this is called the propulsive. Now, if I try to do the same thing for battery driven system, it will be again much simpler, because my weight does not change. I simply have to find out the time of flight. So, just like we did earlier, I mean, I told you that, I mean, I can actually, if I go back to the previous slide, I can get a time of flight versus V infinity formula, and if I multiply this with time of flight into my power, right. So, that will give me my battery capacity, or I can reverse that and I can actually directly get my range as a function of speed. Okay. So, at every speed I have one power value, and that power into time will give me the time which I have to match with my battery energy capacity. Okay. So, let us look at that again. So, this is clear now, all this, okay, fine. So, same power here, yeah, and my same energy content into 10 power minus 3. So, my range we saw is my some velocity, I mean my best range will be at the best range of speed, which basically has maximum L by D. Other than that, I mean any speed. So, I can say that my any range would be any V infinity into T. So, I have to basically find time, and time is same, time is my battery energy content divided by my power required, and power required will be given by this along with my propeller efficiency. Okay. So, this would be E n by P A into eta, because this power required does not include propeller efficiency. Okay. This is only telling me what is the power due to the drag. Okay. So, power due to drag has to be converted to the power required by motor propeller system or power that my battery has to deliver. So, the power that the battery must deliver would have this eta divided by that. So, this PR divided by eta will be power that my battery has to deliver. Okay. So, this gives me the time and this multiplied with my V would give me the range. So, my range R is simply V infinity into eta into my battery energy content divided by my power available. So, there is no mystery here, it is just plain simple thing. So, it is clearly you can see the range will be again a function of my V infinity and one can easily plot a range versus velocity graph also. So, in your next homework assignment I will try to give you some of these tasks to plot some of these graphs and see for yourself, okay, that how my range is going to change with speed, my endurance is going to change with speed, what would I do to maximize it and where would I want to operate for a realistic UAV. Okay. So, I will try to get data for a meaningful realistic UAV and for which we can compute all these things. Okay. And any questions? It is clear. So, here main thing to keep in mind is that understand your battery's number of cells, multiply with appropriate things to get the energy content in joules. Okay. Power in watts is basically joule per second. So, this time t you are getting is actually in seconds. So, you must divide it by 60 and all to get if you want to convert it into hours, 62 convert to minutes and then further 62 convert into hours. So, that is all you have to take care of. Okay. So, we will now move to the next element of our study. So, yeah.
We are considering the communication range to be a satellite based or something?
No. So, this is purely my range capability of my aerial vehicle. So, I am only worried about what my aerial vehicle is capable of. Okay. So, if it is capable of going 100 kilometers, does not mean that my UAV can go 100 kilometers. Why? Because I would need to have the communication setup. So, we are not at all factoring, this is purely aerodynamic performance capability. So, if I get endurance, okay, endurance is again meant for this is the time I can fly for. Now, how far you want to send it across, that is up to me based on my communication range. So, I told you earlier also that communication range, operational range or whatever, it is defined based on other factors, okay, not based on the aerodynamic performance capability of the UAV. See, if I design something which is fire and forget type thing, where I fire and I do not care where it is going, then it can go to the highest possible range, which means I am not really trying to get any communication back from them. So, we had actually Air Force had bought some equipment which were of this kind, fire and forget type, and this particular drone would fly for 6 hours and so 6 hours means it has tremendous range, but it is not necessarily communicating back. Once you have fired, you have no way to know whether it has done the job or not done the job. So, that is a simple thing, but whatever we have calculated, this is purely the aerodynamic based or aerodynamics based or your performance based parameters. It has nothing to do with your actual operational requirements or your operational capabilities. Operational capabilities will be governed by your communication equipment weight. If I want to communicate over longer ranges, my equipment may become heavy. So, which means that I cannot operate it beyond a certain range. So, a lot of small UAVs are there which may actually be able to hit targets much further away, but simply because there is a requirement that it has to convey the information that where it is going and what it is doing. So, that actually puts some restriction. So, that is separate thing, that is purely, but that will be always a subset of this big number. So, this number is much bigger, and if there is a requirement, if I can compromise on maybe my payload capacity and other things, I can always put a bigger communication device which can give me a range of longer distances. And like you said SATCOM, yes, if I am going 1000 kilometers, I will have to use something like SATCOM. So, then in the beginning itself I will try to cater for that weight of my SATCOM module in my design process. So, it is not becoming a burden later on. So, that is something to be kept in mind, fine, alright. So, We will continue with some more performance studies, but we will also need to we will also try to sort of get some sense of structural aspects, because this load factor actually originates from flight mechanics, in the sense when my aerial vehicle maneuvers. See, so far we talked about only steady level flight, but what happens when my aerial vehicle actually maneuvers, which means my UAV has to turn. Now, if it is turning, will it turn with a radius, because when you turn, I mean, you are going in a circle. So, circle will have a radius 50 meter, 100 meter, 500 meter. What should be that? Does it affect me? Does it affect my design? So, this factor, that the moment I start maneuvering, my UAV will actually experience loads higher than what it experiences in level flight. So, what are the loads? Well, one is of course what we have talked about, aerodynamic load. So, aerodynamic load is my lift, drag, and load coming from my propeller, thrust. Okay. So, these are the loads, but now when you maneuver, when you start doing turning flights, you will also have now additional forces coming because of your centripetal acceleration, okay, or which you define as centrifugal force. So, the moment I turn, you always experience centripetal acceleration, right. So, when you are on cycle and you turn, you have to bend. Why you have to bend? Your high school mechanics? Yeah, so you bank, right. So, why do you bank? If you do not bank, what happens? Yes. So, you bank because you basically want to give a component of your friction to balance your centripetal acceleration or cater for the centripetal acceleration, which balances your centrifugal force. If it is not balanced, then it will try to throw you off. So, even when I am sitting in a vehicle and the vehicle turns, I will try to get thrown outboard away from the center. So, which means that now it is creating some kind of force, and this force is getting transferred on the body of the aerial vehicle, but up to what extent? So, this is now the concept of load factor originates from your aerodynamics and your flight mechanics, but it directly affects my structural design. Okay. So, we will not really go into the details of structures, but we will try to relate that, I mean, what it actually poses as the key requirement for your structural design, okay, in the sense that what load factor it should be able to handle. See, when I say load factor means, see, so in level flight we simply said, okay, my structure is supporting the load which is equal to my weight, but when I go to any other flight condition, when I am turning or accelerating or decelerating, my load may increase, but by what factor? Because when I design my structure, I have to design it to cater to the condition where the load should not make it fail. My load should not be so high that it will fail, or my structure should be strong enough to cater to whatever high load it encounters. But if I try to over design it, if I do not estimate my loads on the craft correctly, and I think, I mean, my actual loads are maybe 100 kilos and I think, I mean, the loads are actually 500 kilos, then my structure will end up becoming heavy. Why? Because if I want to make it strong, I have to put more material would be stronger, but then it is unnecessarily strong. My loads are not so high, and if I make it heavy, everything else will get compromised. The moment my craft becomes heavy, my power consumption will go up. My power consumption is a direct function of W. So, if my W is more, I have to fly at higher speed with the same wingspan. Higher speed means higher drag, higher induced drag. Okay. So, everything increases. So, my power consumption is more. More power consumption means I can fly for lesser time. I cannot meet my endurance or my range requirements. So, all this actually becomes very critical. So, the structural design optimization is the key. If I design and make it very optimally, I can ensure that I can get all my performance back, and also my structure would not fail in flight. Okay. So, this is something which is taken from manned aerial vehicle regulations, which is, so FAR actually stands for Federal Air Regulations, okay, which is the document created by FAA, Federal Aviation Administration in America. So, equivalent of DGCA in India. So, similar things would be there in DGCA's airworthiness requirement manuals and standards. So, this actually defines or gives the definition for this flight load factor. It is a new term, may not be familiar to some of you. So, flight load factor represents the ratio of the aerodynamic force component acting normal to the assumed longitudinal axis of the airplane. Longitudinal axis is the axis along the length of the UAV to the weight of the airplane. So, it simply tells that my load factor, which will be denoted by n, is a general symbol for this, not eta n, this is normal n. So, n is defined, it is saying divided is equals to L divided by my W, and it says flight load factor. Okay. So, this is for flight, remember the word flight load factors. Yeah, I mean my load factor can be for non-flight condition also. For example, my UAV is parked on ground. What is the load factor on that? This is flight load factor. I am talking about only load factor. This definition is only true for flight condition. Okay. So, when you are not flying, does it mean that the load factor is 0? So, it is a tricky question. It is something which confuses many people. So, my question is that if my UAV is parked on my ground, okay, on somewhere actually, and I want to understand what are the forces acting on it. Weight, but there is something which is balancing the weight, normal reaction from the ground. So, there is some reaction, so there is some force acting on it, and that divided by weight. So, your normal, I mean, so your load factor will be still 1. Okay, so, under all conditions, I mean, the load factor will always be at least 1. So, that becomes my base load. So, when it is supporting, so my landing gear should also support the weight of the craft, right. So, that is also important part. So, when you are in flight, loads are a combination of your aerodynamic loads and inertia loads. Inertia loads means loads which are coming because of your motion. So, turning flight, climbing flight, descending flight. So, any other maneuver which you are doing, all of that will actually sometimes create additional forces, which you must account for in this, and all of the additional forces are going to come from your lift only, and that is why this definition is fine in flight. In flight, I mean, this lift will cater for your centripetal acceleration, it will cater for your weight, everything else. So, this is the normal scenario. So, these slides I will upload soon, okay, on the Hello IITK for you to see, and right. So, whatever we have defined here, the same thing we will try to represent on a fixed wing aerial vehicle. So, this showcases all the forces and moments, well, forces, not so much moments, acting on the craft. So, I have my lift, I have my drag, I have my thrust, and I have my weight. So, as per the definition of this load factor thing, my lift would be equal to this vertical load factor. So, z is the direction. So, if I say this is my x direction, this is my z direction, okay, and maybe this way is my y direction. Okay. So, n subscript z is my vertical load factor. This would be equal to weight plus if there is some. So, if let us say this is actually on a trajectory which is on a circular path or something, or for some reason there is a vertical acceleration happening, okay, then that part would create a pseudo force. This is your centrifugal force. Well, could be centrifugal force or it could be some other pseudo force also. So, if there is a pseudo force acting, that will be mass into acceleration. So, this is my inertial force per se. So, what happens then? My load factor then or rather my lift is equals to weight plus this additional component, and this component is because of some inertial force. Inertial means due to motion. So, due to motion there is some, so there is some maybe some kind of vertical acceleration happening, and as a consequence of that I get this pseudo or dummy force acting in the opposite direction of the acceleration. So, we are assuming that there is some acceleration A in the vertical direction, which would in a normal circumstance show up when your airplane is trying to go on a climbing flight, climb in a vertical path like this. So, you are climbing on a circular path, not doing a steady straight climb, you are doing a climb with the intent of, I mean, say going in a loop kind of thing, what fighter planes do, acrobatic UAVs can do, or small UAVs can easily also do. So, we are assuming something like that. So, that would mean my vertical load factor is defined as 1 plus the acceleration divided by acceleration due to gravity. So, this is my vertical load factor. and this is actually indicative of how much of additional forces are going to come on my airframe, on my aircraft structure, on my UAV structure, and this is something as a designer one has to cater for. If you estimate it accurately, you can design your structure optimally. Okay. So, this A, depending on that, so if this A is equal to G, then what happens to my NZ? It becomes 2. So, we will call this as 2 Gs. So, that is what I mean your pilots call. Okay. So, they say I mean we are going to pull a 5G maneuver, okay, or 7G maneuver, right. So, that is what they are actually implying. How many load factor or what is the load factor that they are going to encounter. So, my UAV also is going to encounter, but UAVs are not that aggressive things. I mean it is not manually being piloted and it is not going to do some acrobatic flying. It is normally meant to do some sudden mission, go fly here there, okay, loiter around, okay, maybe dive sometimes, okay, so do certain things. But so therefore, I mean your load factors which will be encountered would be not very high. So, 2.5 is typically what you would cater for most of these small UAVs. Okay. Now, that was for a normal translational flight when you are in a straight flight, but with an intention of doing a climb. I can actually have different kind of loads appearing even in normal straight flight also, if I suddenly accelerate, okay, or suddenly decelerate. How? Lot of UAVs which are being used nowadays, they are actually, or especially even fixed wing type, meant for long range operations, kamikaze roles. All these UAVs do not have landing gears, they do not do ground roll, they are simply launched, and launched means either they will be launched through a catapult or through something which is suddenly going to propel it. So, it could be jet assist or it could be some spring loaded mechanism, so or pneumatic mechanism. So, all these mechanisms are going to create sudden acceleration in the horizontal direction, right. So, in normal horizontal flight also there could be a sudden acceleration or deceleration. So, deceleration could be, I mean a very nice example is, have you seen zip lines fixed wing UAV used for blood delivery? The original designs, they used to come down and land by putting a hook on a string. Have you seen that video? It is a very interesting thing. So, they would launch using catapult, it will go and deliver the blood by dropping it, a small parachute, and it will come down to the depot where it has to land, and they actually had a nice mechanism where there is a cable pulled across, and this airplane will drop a hook, okay, which will come and get tangled on this cable, and it will suddenly hang from that. So, it is a very fast deceleration. Okay. So, this is that case which would create now a horizontal load factor. So, this is my horizontal load factor. Those are mostly larger airplanes, I mean smaller UAVs are not yet readily operational on, but yes, it could be relevant there also. Horizontal, by this only, by using this pulley, some kind of pull mechanism, right. So, you
we deploy the hatch and that pendant is there, that hook arresting system is there in beneath the
but
main
for
landing
normal
gears.
landing or for even
For normal landing.
The normal landing also it
For
actually uses
normal
that. Okay. So, it has a arrested landing, that is called arrested landing.
Arrested.
So, this is a horizontal load factor. So, all these things are very nicely described in a old classical book by Perry and I think Azar. It is a book on structures or more on a structural design, it is a very old book, but it is the only book which actually talks about all these load factor business in a very clear manner. Other traditional aerospace books do not talk it that well. Okay. So, this is a horizontal load factor, which means there is some horizontal acceleration which is going to create sudden loads, okay, and you have to cater for that. So, this arrestor mechanisms, they are connected to some point which actually has to be stiffened and strengthened. So, those points where these arresting mechanisms are connected or where your pushing mechanisms are also connected. Okay. So, you are trying to push your vehicle, all these areas where this force will suddenly come has to be made in a proper manner and with proper analysis to make it strong enough that it will not get damaged at the time of taking off or at the time of landing. So, here what we are saying? We are saying okay, I suddenly accelerate or decelerate. So, there is some horizontal acceleration. So, there is a corresponding force because of that. Yeah, so this W by G is simply your mass. W is coming because I mean I am trying to define my mass. So, weight divided by G. So, this is simply m into Ax, which is my horizontal force. I am assuming that my acceleration Ax is in this direction. If it is negative, then the sign will automatically change. So, I am accelerating forward, this will actually try to create a backward load, right. So, that is what is max, which is W by G Ax, and this would be equal to, now this acceleration deceleration we are assuming is coming from my propeller, but there could be some other mechanism also. So, that is why we are saying T minus D by W, but instead of T I could actually have a separate mechanism like a catapult thing, which is using pneumatic force to suddenly accelerate mine. So, all this actually creates a certain higher load in the horizontal direction, and I may have to use this in my analysis to ensure that my structure is going to remain safe and not break apart under this kind of load condition. So, same thing can be extended for a more general flight where I could be actually in a say dive kind of scenario, and I would have probably both horizontal acceleration vertical acceleration and horizontal acceleration. So, here I have my airplane. So, let me draw okay. So, that is my airplane. So, I have my thrust force and so all these pictures are from my reference of this Piri Renaza's book. Okay. Yeah. So, my W, and I would have drag force, lift force, weight is here, and so if my aircraft is, this angle is theta, then this becomes my W cos theta, and in this direction I will have some acceleration W by G A Z. So, now my axis is, yeah, this is x direction and this is my z direction as earlier, and I may have some pseudo force in this direction W by G into Ax. Okay. I think all the things are shown now. Yeah. So, one can again take the force components along the x direction and along the z direction and write these two equations, assuming your equilibrium in z axis and equilibrium about x axis. So, we can say, you can call this as linear momentum balance, linear momentum. So, this is Newton's law, balance about x and z axis. So, first about z axis. So, my lift force, which by definition should be equal to n z into W, will be equal to m into A z plus W cos theta, and similarly here W by G into Ax, which is T minus D by W and all that. So, I get this two formulas, one for my load factor along the x direction and load factor along the z direction. And if I want to find out the total load factor, that would be right, because these are both normal to each other, perpendicular to each other. So, this is for landing, this is for angular motion, okay, fine, yeah. So, yeah.
Y axis. Any reason why we are suddenly switching to Z axis?
Which is y axis? Vertical. I mean, you can call any axis anything actually, it's just that I mean this book has followed one convention, okay, but normally Z axis is vertical, it is not y axis. Okay. Vertical axis is always Z axis, okay, in most body axis definitions.
So, its pitching was along the Z axis.
No, never, no, that is y axis always. Where did I call, I mean, in plane axis is y axis, sorry, z axis, no. So, I mean traditionally any aerial vehicle, okay, if I again draw aerial vehicle, so this direction will be always x. Now, z could be up or down, yes, up to you, mostly up and this will be y. So, this is the convention which is always used. Okay. So, your pitch is about y axis, not about z axis. Your z is always about your yaw. Okay. So, if we look at, I mean, the conventional names for my forces and moments. So, we have Fx, Fy, Fz in the body axis, and we will have Lmn, okay, where this is my roll moment, pitch moment, yaw moment. So, this is about z, this is about my y, this is about my x. So, L is actually, capital L is basically my roll moment is called by this. Okay. So, one can also call this as Mx, My, Mz. Okay. So, this is how it is. Okay. I mean, your z axis is always up or down, vertical axis. So, similarly one can do for landing also, not very important. If I am coming for landing and my wheel touches down, so all the reaction will come from that. So, you could have some load factor because of this, not that critical. So, just these two formulas you can get by doing the equilibrium in the x and the z direction again, and your x load factor, z load factor will be vertical reaction by W, and your horizontal load factor will be horizontal reaction by W. Okay. So, this is vertical, this is horizontal, and this is not that critical because we would rarely worry about this. For a larger UAV, probably yes, if you have a MALE or HALE class UAV and you are worried about its landing and the impact landing. So, the impact loads which are going to come, I mean, that you will get from this, and this could be relevant for your landing gear design if you are trying to design the landing gear. So, then this becomes important there, okay, because what kind of sudden acceleration you are going to experience. Okay. Okay, so fine. This part I will skip, not critical. This is load factor due to angular motion, rarely considered. So, it will be there in the notes, but we will not cover this. Okay. So, now that we have at least got some definition of N, that is my load factor. So, the symbol is N. Now, the basic, right. So, this slide says design flight requirements for aerial vehicles, where we say basic strength and flight performance limits for a particular aircraft are selected by airworthiness authorities and are given in the form of flight envelope. What is flight envelope? This we commonly call as VN diagrams. So, V you already know is your flight velocity, right, and N is the new thing we are learning, which is the load factor. Okay. So, Vn combined becomes velocity load factor diagrams. Why and how we will go into the depth of this actually, that what exactly it implies. And so, even if you go and look at DGCA's regulations for getting a UAV type certified. So, a lot of small UAVs you do not have to go, and even if you are going to use it for defense applications, CEMILAC is saying any drone which weighs less than 150 kilos, you get it type certified from DGCA. And once that is done, I will probably ask you to do some more tests and I will give you a certificate that it is fit for defense applications. So, that is what CEMILAC says. Okay. So, DGCA in its type certification process, they also list out certain load factors for which your structure must be able to handle. And unfortunately, they have not really said, I mean, go and look at VN diagram, that your load factor as a function of your speed, but they are simply as a rule of thumb they said, okay, fine, you design your structure for whatever condition you fly at, whatever speeds you operate at, you must be able to, your structure must be able to withstand this certain load factor, which I think is 2.5, I will double check it, but if I remember correctly, that regulation says your structure should be able to handle load factors up to 2.5 G, 2.5 times G. Okay. So, we will continue from here in the next class, because this will also require some elaborate discussion to understand this whole concept, because a lot of you are from non-aero background and also from mechanical and all. So, this idea is very, very new, and we will try to take it slowly to for all of you to digest it. Okay. All right, so stop here. Any questions?
And on the same book, Perry and Azhar.
So this, I mean, these slides, if you, these few things, if you want to have better understanding, you can go and look at it. But otherwise, you don't have to go and read that book per se. Just this part, if you want to read, you can read. Okay. Yeah. So this part, if you need further clarity, you can refer to that book. Yeah.
Translational flight, we are saying thrust equals to the drag. Is it if we equal the thrust to drag, is it a condition like the flight will only take off and not move in a forward motion?
No. So this is talking about thrust equal to drag is only when you are in steady level flight. Steady flight when there is no acceleration, you are flying at a constant speed. We are not at all talking about the takeoff and landing part. The takeoff and landing part is where you are saying, okay, now my thrust is not equal to that. I am actually accelerating. So I am starting from 0. Okay, my UAV starts maybe moving on a catapult or hand launch or ground roll, right. So if I am doing a ground roll, starting from 0 and then picking up speed to go faster, right. Okay. Today is, yeah, level flight, steady level flight means, I mean, you are going at a constant speed.